Well, this is Green's theorem discussed in the last video. Let R be a simply connected region with a piecewise smooth boundary C that of course doesn't cross itself, oriented counterclockwise. Means the curve is only traversed once, and the interior of the curve is always on the left of the curve. Like the purple region above here, we saw in the last video, that would be describing that type of curve. Notice always the curve is on the interior, right? Or the connected region is on the interior of the curve, on the left side of the curve. Okay, if M and N have continuous partial derivatives in an open region containing R, then the line integral of m dx plus m dy, which we've seen before, is equal to the double integral over the region R of the partial of n with respect to x minus the partial of n with respect to y dA. And again, we find dA and the region R's limits like we did in the last chapter. There is a proof in the text in any good multivariable calculus text, so I won't repeat it here. But let's do an example. Use Green's theorem to evaluate the line integral of y cubed dx plus x cubed plus 3xy squared dy along the path from 0, 0 to 1, 1 along the graph of y equals x cubed. In other words, it goes from 0, 0 to 1, 1 along y equals x cubed, and then goes back from 1, 1 to 0, 0 along the graph of y equals x. And so our partial of n with respect to x is 3x squared plus 3y squared. That's the partial of this n with respect to x. And the partial of the m with respect to y, of course, is 3y squared. So by Green's theorem, we know that the line integral of m dx plus n dy is the double integral of partial of n with respect to x minus partial of n with respect to y dA. So this region M here dictates our limits of integration. See, the region is this one. It would go out this way and then back this way, back to the origin again. So the upper part, of course, is x. The bottom part is x cubed if we do our stripe across the region. And here are our partial derivatives. See, we already calculated that. And so it would be this. And of course, I didn't say anything about this, but we'd be making these stripes across here from x equals 0 to x equals 1. So the limits are y equals x squared to y equals x and x equals 0 to x equals 1 of these partial derivatives. And of course, integrating with respect to y, if you notice this part and this part subtract off and make 0. So it's just integrating 3x squared with respect to y, we get 3x squared y. And that would be evaluated between x cubed and x. So we get 3x cubed minus 3x to the 5th, if my algebra is correct. And then that would be evaluated between 0 and 1, and I'll save you the arithmetic on that one and just say I'll let my software do it, and it comes out to be 1/4. Well, here's the same problem without using Green's theorem, and we need to add up both line integrals along C1 from 0, 0 to 1, 1 along the path y equals x cubed, and also along add up to that the line integral along C2, the path from 1, 1 to 0, 0 along the line y equals x. In other words, we have to add up the line integral along here plus the line integral along here. And if we did that very thing, right? See, this describes it in a line of math. So the curve 1 is described by vector valued function ti plus t cubed j, at least that's the easiest way to describe it, t going from 0 to 1, and then that integral would become from 0 to 1 t cubed cubed dx, so we'll call it t cubed cubed, that's t to the 9th, I guess, dx, and then t cubed plus 3t times t cubed squared. Where did that all come from? That all came from, well, here it is. It came from here. Here was the, remember, y, our y of t is t cubed, so that would be t cubed cubed dx. Dx, of course, is just 1. And that here would be our x cubed plus 3x, or 3t, right? T cubed plus 3t times y squared, which is t cubed squared. That's where all this mess came from. And so we do wind up with, I won't bore you with the details of this integration because it's just common calculus 1 integration here. We do wind up with 3/2. Keeping in mind our answer is supposed to be 1/4. So I hope when we come back along the other path, right, we'll get something like -5/4 or so, because we do want an answer of 1/4. So when we come across the other path, 1 minus ti plus 1 minus tj, t going from 0 to 1, that's a little tricky, but that would work for the path starting here and ending up back here. That's why we have to have it 1 minus t. And so our y cubed is replaced with 1 minus t cubed times dx would be, of course, derivative of 1 minus t, which is -1. And then x cubed, 1 minus t cubed, plus 3x y squared, there it is, times -1 dt. And this is just a big algebra and calculus 1 problem. I won't bother you with it, but it does come out to -5/4, just like we expected. See, the -5/4 plus the positive, whoops, where I went too far, plus the positive 6/4 we got adds up to the 1/4. And if you were to ask me, I would say it sure was easier to do that one as a double integral, and that is what Green's theorem says.